this concept of conservation of momentum is not very useful, because it is very obvious if no external force is acting, then the momentum of the particle doesn't change. So if there is only one particle involved, in the impulse principle may be useful if force is given as a function of time, we integrate that to find the final momentum. But if impulse is 0, the conservation of momentum principle for a single particle, the law is not very useful. The conservation of momentum principle so if we write the conservation of momentum principle, this is useful if we have more than one particles involved. So then as we have seen the example for energy which we saw, there were two blocks, and if we consider both of them together as a system, there are cases like that where we have two particles which are there, and in there if these two particles are interacting, then the principle of conservation of momentum can be useful, and we will see how it is done. But for that to be useful, what we need is Newton's third law, which tells us the forces between these particles are equal and opposite. So when we consider both these particles together as a system, then the internal forces between them will not matter, they will cancel out, and we will just talk of external forces acting on the total system. But before we do that, we introduce another concept. We introduce a concept of instantaneous impulse. And instantaneous impulse means if a very large force acts on a particle for a very small time, then the impulse of this force is said to be an instantaneous impulse, and this force sometimes is referred to as an impulsive force. So now let us just try to see mathematically what this means. So what we are now defining is, we have already defined this quantity impulse, let us say INST, which shows an instantaneous impulse. This will be integral from T1 to T1 plus epsilon of integral f dt, where when we take the limit, epsilon tends to be 0 and f tends to be very large, which means we can idealize it to be going to infinity, and if the average value is of this force is f average, which is large, and we are multiplying it by T1 into T1 plus epsilon, which is basically epsilon, this delta T is nothing but epsilon, which is very small. So this product is like something like infinity being multiplied by 0. This will be a finite product, and this is what we call as an impulsive force, and the impulse due to this force is what we call as an instantaneous impulse. Is this just a theoretical concept or is it a practical concept? And let us give a couple of examples, both of which are very similar. The first one, let us take the case of Roger Federer hitting a tennis ball. Let us say Nadal is serving, the ball comes and Federer hits the ball with his racket. Now the time of contact between the ball and the racket is very small, and the contact force is very large. So, such a force is an example of an impulsive force. Force which acts for a very small time, but the force is very large. And what is the effect of this force? Let us see. The ball is coming from this side till it hits the racket. And so, when the ball is coming, it is coming with some momentum. And the racket applies a force on the ball. And what is the net effect of that? So, this force plus the impulse will be equal to the final momentum. And the final momentum is nothing but the final velocity of the ball multiplied by its mass. So, therefore, whatever force Federer applies on the ball with his racket is what gives the new velocity to the ball. And it has a twin effect. First effect is it's coming in an opposite direction. First it stops it and then it makes it go with a very high velocity on the other side. And so this contact period and this contact force is what we are calling as an impulsive force, and the impulse is what we are calling as an instantaneous impulse. And a second example of this could be a very similar example when Virat Kohli hits the cricket ball with his bat. Once again, the ball is coming, the bat changes its direction, bat applies a force because of which the ball changes its direction. So, what we see is the effect of the impulsive force is one, the direction of the particle could be changed, and secondly, the speed of the particle is also changed. So, either one or both of these effects could take place, and this is what the impulsive force or any force would do on the particle. Now, when an impulsive force acts, on a particle, other finite forces may also be acting during this interval. When an impulsive force acts, it is possible other forces are also acting. For example, when the tennis ball is coming and is being hit by the racket, gravity is also acting during this time. But because the impulsive force is very large and this force is acting from T1 to T1 plus epsilon, a very small period of time. So, during this time period epsilon, we neglect the effect of the other finite forces. Notice the effect of these other finite forces is only being neglected during the time period epsilon. Before time T1, the trajectory of the ball is governed by the finite forces, for example, the gravity acting on the ball. And after the time period T1 plus epsilon, once again the impulsive force is not acting, so the motion of the ball will be governed by its initial state and also of the finite forces. But during this interval, while the finite forces act, we neglect their effect. And this graphically we can show very easily. Suppose if we draw force versus time, let us say this is gravity force which is acting on the ball, there is some other finite force, it may be some other force which is of the same order, and the impulsive force which is acting, it will be 0 up till time T1, and at time T1 a very large force acts and it stops. So, this time is T1 plus epsilon. So, what we are saying is during this time period from t1 to t1 plus epsilon, only the effect of the impulsive force is counted. We do not count the other effect, and this is very clear that if we look at the change in momentum, it is due to impulse. So, this area will be much larger during this interval epsilon than the areas by gravity and all, and as epsilon goes to 0, these other force, the impulse will go to 0. So, therefore, we just use this. Now, sometimes in the problem you are asked to find the average contact force, F average, and if the time of contact is given as delta t, so then what we have is F average times delta t. Now, when we talk of F average, that means what we are saying is this average force is acting over the entire period delta t. So, we treat F as a constant, and this must be equal to the change in momentum. So, if we know P1 the initial momentum and the final momentum P2, this P1 just to recall is mv1, this is mv2. So, if we know these, then we can find the average force. So, if you want to find how much force does Kohli's bat apply on the ball, for that you need to know the initial momentum of the ball, the final momentum of the ball just after he has hit the shot, and the difference of these two will tell you how much force. And if you have an estimate of the time of contact during which the time for which the ball has been in contact, then you can find the total force. Okay. So, now let us see how this principle of momentum can be used when we have more than one particle. And this is what we said, that this is where we will have the, we could possibly use not the impulse principle, but the principle of conservation of momentum. Now, what are the type of problems where we will have more than one particle where such things could work out? One of the very typical problems which we have are what we term as collision problems. That means we have a body of mass m1 travelling with a velocity v1, and we have a body of mass m2 travelling with a velocity v2. These two, this is what we can call as the pre-collision stage. They touch each other. So, this is at a velocity v1, this is at a velocity v2. They hit each other, and this is what we will call as the collision stage. And after they have hit each other, this goes with v2 prime, this goes with v1 prime. These are the final states, and this is what we can call as the post collision. So, this could be one state where we have more than one particles involved. The second type of problem is when we have one body which is moving and it suddenly breaks into two or more parts. So, it is something like a splinter which is moving and then it breaks into two parts. So, this is MA and this breaks into two parts B and C. Now, this breaking up will be because of internal forces, and then we can let us see how we can apply principle of conservation of momentum. Now, in these, if we treat, so that means we have more than one particle. If we treat both the particles, so let us take a case of two particles, and we treat both the particles as one system. And let me first state the principle. if no external force acts on the two particles, then the momentum of the two particles as a system is conserved. So, first I have stated this principle: if no external force acts on the two particles. Now, by external force, force which is external to 1 and 2. So, we will just show how this works, but the principle says then the momentum of both these particles together as a system is conserved. So, let us say we have a particle A and on which an external force Fa is acting, and we have a particle B on which a force Fb is acting, and these particles maybe they interact with each other. So, let me show them close to each other, and maybe they are hitting. On this external force Fa is acting, on particle B force Fb is acting. Now, if I draw the free body diagram of particle A, then free body diagram of particle A will show me Fa. Now, I have to show all forces external to particle A. Now, particle B, suppose these are touching each other, will exert a force on particle A, and let me call this as Fab, the force Fb, and then on this I will have Fba. This is the force exerted on B by particle A. Now, when we add up the two systems, and what do I mean by adding up the two systems is, let us add up the forces acting on the two systems, because we are considering both of these systems together. Then what will happen is, we realize we have Newton's third law which is there, and Newton's third law tells me Fab is equal to minus of Fba. So, the internal forces which exist among these two particles, they will cancel out. So, now let us write the impulse momentum principle. So, what we will have is the impulse momentum principle for particle A, that will tell us integral Fa dt plus integral Fab dt is equal to change in momentum of particle A, and impulse momentum principle for particle B gives me integral Fb dt plus integral Fba dt is equal to change in momentum of particle B, and when we add these two, what we will get is integral Fa plus Fb dt plus 0 is equal to change in momentum of particle A plus change in momentum of particle B. And if, so this is the total impulse momentum principle applied to each particle and added up, and if Fa and Fb both are equal to 0. This is what we said in the law of conservation of momentum, that external forces to the system. Now, we have particle A and B, external forces to the system are Fa and Fb. Now, these could be because of any external things. If this is equal to, then if Fa plus Fb is equal to 0, so if these forces are equal to 0, then the change in momentum of particle A plus change in momentum of particle B is equal to 0, and this I can write it as ma Va plus mb Vb at state 1 is equal to ma Va plus mb Vb at state 2, and this is what we call as the law of conservation of momentum. And this, as we said, this could be used if we have impact problems, collision problems, then if external forces are 0, then we can use this. And as we have seen, in some cases external forces may not be 0, but in a collision, let us say when we talk of a collision problem, during the collision period, the collision forces are much bigger than